Go.
Okay, so let's go ahead and get started. So I'll be talking about interactive realities and creative spatial interfaces today. So one thing I want you to do, and I purposely have no visuals here, is to just think about a place that you really enjoy, that is your happy place, if you will, and think about or imagine what it is you're seeing, what it is you're hearing, what is you're maybe smelling, what it is you can feel in part of that environment, maybe even what you can taste. So if I think of the beach in this snowy weather, if I can hear the waves, I can kind of smell the seawater, I can maybe touch the sand and feel the grains of sand between my hands and my toes. Maybe I can even taste some of the salt water. So this, if we imagine this environment, we can almost feel like we're there. And that's what we might call a sense of presence, how much we feel that we're in that environment. And we can do this just through kind of meditation or imagining these things. And if you're imagining somebody with you, that might be a sense of co-presence. And so when we're part of these environments, virtual reality offers technology to help transport us to these interesting worlds, whether that be a replication of the real world, whether that be an imagined virtual world. And then augmented reality environments try to kind of add to what it is in the real world. And so in these environments, one of the things that I'm interested in is how we can do tasks better in these type of environments. And so in particular, my passion for research is to design 3D user interfaces to improve interaction in these virtual augmented mixed reality systems. And so I'm just kind of highlighting improve for a second, because what do we mean by improve? How do we improve interaction, or how do we create better interaction? And so I'll be kind of touching on some of my work that explores that. And so to understand a little bit about what some of my work is done in the past, if we look at 3D user interface tasks and general tasks that you might evaluate an interaction technique or input device, and those traditional tasks are selection, manipulation, and navigation. Selection is the idea of identifying something you want to interact with it further. Manipulation is the idea of taking an object and doing something with it, but very specifically translation, which is changing the position, rotation, and also could be scaling, so changing the size of the object. And this is done in a number of virtual and augmented reality environments. And the last one is navigation. So how do we get from point A to point B? That's travel. And then what are the cues that help us get from point A to point B, which is wayfinding? And so often 3D user interfaces are evaluated against these very core foundational tasks. And I'll get to later why I'm kind of pointing this out. But so some of my past work has focused on, when I evaluate our interaction techniques, they're evaluated against a subset of these tasks. Okay, so the first thing I want to talk about is some of the interaction techniques that we've worked on over the years. And when I say we, I'm talking about my students and I at the University of Wyoming at the Interactive Realities Lab. And so these are just a subset of the work that I've done to kind of show you the type of work that we've worked on. And a lot of it focuses on quantitative evaluation. So very much, taking a specific research question. When we conduct the evaluation, we might be comparing techniques and identifying the differences between those techniques. We might evaluate them against some benchmarks and get some performance benefits. Okay, so let's play a game. So I want you to actually reach out and try to grab the object that's you feel is furthest away from you. So go ahead and do it, reach out and grab. And those on Zoom, camera off, you can do that even more, no one's gonna see you. So which one did you grab? Just shout it out. The green one that was furthest from you?
I grabbed the yellow. Oh, orange. Yeah.
Smallest ones.
A small one.
Yeah, so the smallest one would be the one that would be perceived as furthest away. And I color coded these because I had no idea how Zoom would represent the left and right on this. But anyway, so this is a known illusion called the Ebbinghaus illusion. And the idea is that cues around an object look different depending on, objects in the middle look different depending on the cues surrounding that object. And in particular, larger cues that are around the object make the object look smaller, and smaller cues around the object make the object look larger. And these are very much the same exact object. And I know that because I copy pasted the object in the PowerPoint slide. So given this illusion, we want to understand if context cues in a virtual environment can change the way we perceive objects. And why is that important? Because when we're reaching for objects, we're interacting with objects, we need to be able to understand or perceive the appropriate distance that we are from that object to be able to interact with it well. So one of our studies that we have conducted is to evaluate these type of perceptual illusions, and specifically the Ebbinghaus illusion, for 3D user interaction. So if we go back to our reaching game, so if we look at when we go to reach for an object, we're actually doing some planning, even if we don't realize it. So there's a step before where we kind of are gauging what direction we're going to reach for the object, and our hands are adjusting. And so let's look at that in in sports when they do the slow motion replay. So as we're reaching for an object, our hands adjust to where the object is and where we perceive it to be. And we do some fine detailed adjustments at the end. So let's look at the adjustments at the end. And so we looked at this exact task, so reaching to grasp an object. And I just kind of want to point out some things that are important to understand the representations here. So on the orange ball, this is actually the object they're reaching to grasp for. And then we have representing the fingers and the arm of the user or the participant, these smaller colored balls, blue, green, and red. And those were just to give some representation of the hand without giving the full model of the hand, because we didn't want the hand model to influence the perception. We just want to understand the information about the Ebbinghaus illusion. Okay, so and if we look back at my reaching example, closer look into what the green and blue balls are, those are the index and thumb fingers. So we looked at several things in a series of studies. One is we wanted to make sure that the Ebbinghaus illusion was or existed in the virtual environment. Others have looked at this with using disks, but not necessarily three-dimensional objects. So first we checked whether they were able to judge the three-dimensional object, and that's without inducers, with large inducers, and with small inducers. And so what we found was that in the, zooms in my way, in this particular study where we're trying to just see, is there an Ebbinghaus illusion effect at all? And it turns out there is. We would expect that. So where there were objects that were small inducers made the object look larger, they judged the object as larger. Where there were large inducers made the object look smaller, and they judged the object as smaller. Okay, so the next thing that we wanted to look at was if while they were reaching to grasp, if the small inducers or large inducers, would that change the way they were reaching to grasp for the object? Could that change their how they were moving towards the object, how they were adjusting their grasp aperture towards the object? And so what we found was that there actually was some small differences, but not significant, in terms of how the inducers affected objects and how you perceive them. And so in particular, what was happening here is that the objects, we're looking at the dynamic change in the objects, whether they were appearing or disappearing. And so they would either be, they would appear when you started to reach, and then in another condition, they would, you would not see, or excuse me, you would see them, and then they would disappear as you get closer. And so far, what we found, there were not really any differences in terms of the Ebbinghaus illusion affecting that. And in looking at the small and large inducers, you know, we see similar grasp apertures as the control. And so one other thing that we looked at was, okay, what if those inducers swap? So maybe you see the large inducer first, and then as you get closer, it swaps to small inducers. And then vice versa, if you see the large inducers and then they swap to the small inducers. And so what we actually found was that, oops. So what we actually found was that the distance perception changed. So when the objects were large inducers and the object appeared or perceived to be smaller, participants grabbed at the normal distance. But when the inducers were smaller and the object appeared larger, the participants were actually grasping at objects closer to them. And so that actually, that's something that we would expect. And so one thing that, you know, we want to evaluate when we're looking at this is, what did we really learn? And how does that apply to 3D user interfaces? And so we could summarize this as, okay, so for virtual or augmented reality environments where you have contextual information, whether that be labels, signage, could be wayfinding cues, maybe menus, buttons, and widgets, where the objects, where you're not performing an action on an object, so you're just passively looking at these objects in virtual or augmented reality, this can and will change the perception of those objects. And you might perceive the size is different, and in turn, you might perceive an incorrect distance to that object. However, when you're interacting with these objects and you're actually performing an action on those objects, the contextual cues or information around those objects will not influence the perception of size because of that action that you're performing. And so what's kind of an open question still is that, you know, an action a physical action, or is that could be an imagined action? So some research in perception of an action is looked at even just imagining some of these things can trigger those results in perception and action. So there's more work to be done in there to fully understand. And one more thing that was kind of small that we learned, but also interesting, is that there's a value to having some representation of the hand, whether that being a sphere or it could be full hands, only when you're adjusting at the end of the grasp. So you could have, if you didn't have your hands visible, your virtual hands, you could have them appear at the end when you're about to grasp the object. Okay, so something else that we were looking at was, okay, if we're looking at visual perception, we want to also maybe look at how visual and tactile information change how you're interacting with an object. So in one particular study that we looked at when the visual textures are mismatched with the tactile cues of the texture. So if we look at this here, and so we could play another game. If you look at these images, you could think about how some of these textures feel to you. Maybe because you've experienced the sensation in the real world for textures that look similar to these. So some of that you can kind of compare with your past experiences. And so there are a number of ways to represent texture virtually or simulate the sensation of texture. And so we want to know, you know, one is that we know there's the idea that for static textures, visual cues are more dominant. So you might be, you know, maybe you'll have a smooth surface, but the visual cue could give you some information as far as how to sense the texture, how you might feel the texture. But that's for stationary objects. So we didn't, at the time, we didn't know much about objects that are moving. So we wanted to know, does that change? And what are some of the parameters for understanding that? So we looked at one thing that we looked at as far as if you had a moving object, you're going to place your hand on it and feel that texture, how would you perceive that texture? And what if there was a mismatch between the texture and the visual? And about the same time, Benko's work on haptic revolver came out, where it was kind of giving texture information using this device. And so it was really important to understand, well, what kind of information is being perceived with the tactile versus the visual, if that device is not perhaps lined up very well, or maybe you don't have availability to all types of textures, and so you have to use some texture props to represent different categories of textures. And so we looked at, okay, if there's a misalignment in the movement of the texture, we looked at speed, and we looked at how this influences your ability to determine or guess which texture it is. And so one of the things that we found is that we can accept a small amount of mismatch in terms of directionality. And we only tested 0, -30 and 30 degrees, and -60 and 60 degrees. So somewhere between 0 and 30, 0 and -30 degrees, where we start to lose the ability to differentiate. So more research needs to be done to figure that out, but we know at 60 degrees, we don't really have a good ability to differentiate between the the mismatched textures. And then we also looked at speed. And so anything above 8 centimeters per second, we as humans have a harder time discerning between the tactile and visual cues when they're mismatched. Okay, so what did we learn? So if we could summarize this and apply it to 3D user interfaces, you don't necessarily have to have physical textures aligned exactly with the virtual object. And somewhere less than 30 degrees, more research needs to be done to figure it out. But somewhere below that threshold is where, you know, exactly we don't have to have things exactly aligned. And then we also can, you know, if for higher speeds of moving objects in the virtual environment, we don't need exact physical textures and they're less discernible. Okay, so the next thing we looked at was, you know, how we can change the representation of the movements of our body to perform different actions in the environment. And so one of the things in existing literature, this is not our work, but researchers looked at, could you control a third limb using your existing limbs, and proved to be very successful with that. And so one of the things that we were thinking about was, how could you maybe reduce fatigue in this reaching arm movement? You hear about gorilla arm fatigue, to basically translate, rotate, and scale. So some of the tasks that I mentioned earlier with your hand, but instead use your fingers. So if you could take existing limbs and control an additional limb, could you take existing fingers and control various movements? And so our focus was the translation. And so we wanted to divide the tasks of translation along X, Y, and Z axes across various finger gestures. We looked at several different configurations just to start. And, you know, some of these are where you might control the Z-axis translation with your 3 fingers. One thing that we learned in talking with kinesiologists, that your right 3 fingers, although if you could do a static gesture, can be moved independently. When you're moving or controlling, it's harder to separate those fingers. So you could try to do that in your seats if you want. It's a little harder. So they like to move together. And then controlling index finger and the thumb finger with X and Y, or just using thumb in different directions for X and Y. And the other is using whole fist. And so let me show you what that looks like. So this is using those finger gestures to control the translation of these objects in the environment. And so using fingers to move it in and out of the Z-axis, the right 3 fingers moving the wrist to control X and Y, and using the thumb gesture to control up and down. Oops, okay. So this was a very preliminary exploration of feasibility. I wouldn't be able to generalize any of these, but it's interesting to just look at some of the configurations are more fatiguing than other just within the finger movements. Obviously, more data collection and evaluation need to be conducted to understand this further. But more recently, I've been thinking about you know, how this applies to moving full arms. And so if you could use your fingers to control your arm movement translations, and then reaching gestures and grasp. How could you do that, first of all? Is it feasible? And then what are the trade-offs between reducing that physical fatigue from arm movement to finger movement, to the increase in cognitive demand and having to control these movements with the fingers, which is not something we do on a regular basis. And then to what extent could, if this works, could this be applied for individuals with reduced mobility in their arms? And could this be one way to kind of allow or enable and enable users who are not able to maybe perform more natural interaction in the VR environments to do so? And one of the things that that I've worked on in the past is for helping. I worked with someone who was building a startup company in Laramie, who was working on devices that would help individuals with Parkinson's disease and had tremors in their hands to work with mobile devices. So not all mobile devices, new technology actually can go backwards. So the actual push button phones were a lot better for those individuals. And so we were exploring and evaluating different ways in which a new device that would be placed on top of the mobile device would then work to stabilize their motion on the touch-based device. So that was a very interesting project that I learned a lot with working with individuals with reducing mobility. Okay, so the next project is the evaluation of using props as memory aids. And one of the things that I've worked a lot with is with users in cave systems who are exploring visualizations or immersive visualizations and having to do various tasks in those environments. And we were looking at various props to help with interacting and slicing various visualization representations. And this is something that where you wear this kind of bracelet on your arm, and you can, each one you can assign various amounts of the slices to. You can take off, put on the other arm, and you can look at it, rotate it, and it's tracked. That then you can kind of look at the underlying disks and colorization represented by the data. And you can do some gestures where you can change the visual representation of that data as that interaction technique. And we explored with various types of representation, both virtual reality, and then this is the augmented reality version. And so that led us thinking to how could we use props in a virtual and augmented reality. And one thing you might be able to do is to kind of couple those with menus, buttons, and widgets and things like that. And so one of the questions that we had were, how can you better remember the various menus and buttons and widgets using these props? And we wanted to look at, well, if you had these props relative to you, which is egocentric, versus relative to the world, exocentric. So these are in the world, kind of like in the 2D systems where we have the menu bar at the top, and that's in our world to interact with. And so what we actually found looking at those is that egocentric props, and we looked at whether they were in the same room or not, or different rooms. That had no difference. But what was different is those props that you wore, you were able to kind of do the task and retrieve the menus, buttons, widgets faster than exocentric, as well as you're able to remember more from the environment. And in this case, it was actually producing less cognitive demand using the exocentric as well as across the dimensions of the NASA TLX workload, other dimensions of workload. And so what does that really mean? So if we're using menus, buttons, widgets in the virtual and augmented reality environment, we want to store them in an ego-centric because they're easier and faster to retrieve. So one of the things I want to talk a little bit about are some input devices that we created. And so this is the another dimension of my research where I'm very interested in how can we, you know, if the tasks are not available in the existing input technology, what can we do to change that? And so one device that we looked at was, or created, was a squishy device. And so if you're looking at things like modeling or interacting in a way that's similar to sculpting, we were thinking about, well, how could you do this with a device that would allow you to actually deform the material of the device? This idea is not necessarily new. So there have been some past work with foam technology. However, one of the things is that fabrication of this is very complex and takes a long time. And so the other thing we looked at, okay, what about silicone? And in this case, the solution is using cameras. And so we didn't really want to use external cameras because what if you want to use it on the go? And then the other thing, other existing work was done with electronics in the silicone. And so we were also looking at, well, can you do this with something where maybe the electronics aren't as embedded inside and you could actually do something with the volume. And so that led us to kind of prototyping squishy volumes and investigating not just the device itself, but the deformation of the material at various thicknesses. And just to kind of show you one snapshot of this, again, I'm not going to go into full detail, but we were able to see deformation differences based on where you were pressing within the grid. And then, so we also wanted to look at, okay, what if it's in spherical form? Will this even work? And so prototyping it worked in the sense that we were able to sense deformations and spatial deformations, but there's a lot more work to be done in that area because I think if we could get to this vision of being able to hold the object, squish it, and manipulate it, maybe, you know, even have some sculpting tools where we're dividing and scraping to make this tool more useful. Another device that we came up with, this kind of came out of working with those cave devices, cave displays, and you kind of go into those cave. A cave is a 4 or 6 wall display where it's immersive in the sense that it's projecting in stereoscopic. And typically you have joystick controllers, but that's maybe all you have. The space is empty, kind of like the BBX, the Black Box Studio. And so you walk in there, maybe you don't have anything or anywhere to put down your devices. Maybe you want to do some gesture-based interaction. Maybe you want to do some things that you're leveraging physical, some physical prop or things like that to have better precision. So you don't really have that. It's just this open space. So that's kind of where this came about, to create this device that you could take advantage of touch-based input where it leverages physical. So you could kind of walk in there. You could kind of use your pants as a input. You can use your hand as input. You could use props and trace those props. And so some existing work existed, but not something to where it could support three dimension. It didn't have, you know, there were some limitations on the sensors, and mostly not giving 3 dimensional interaction, but rather just texture information. So this was the device that we created, and I'll just show a video of it. So here you're able to do traditional two-dimensional tasks, but then you could also use your hand and touch on your hand. And as you change the rotation, you're changing the device in 3D space. And so you could just use it as a tracker, or you could track different gestures on various surfaces. And so the other really nice thing about the device and how it's worn is that you can still interact with it and hold other objects like joysticks or spatial mice or things like that that you're interacting with. This is showing tap gestures, double tap, and menu interaction. Fast forward to holding a device. So here you see we can hold other devices while we're using it. Okay, so I'm going to not go into too much detail, but we looked at various interaction techniques and form factors, and also evaluated the device itself. But I'm just going to skip through that. One more device that we looked at, Kinetic Skin, is actually inspired by sensing kirigami. Clement Zhang came up with a way to provide input from using paper, using conductive trace. And so the idea of folding or bending that paper, you can then provide input to the computer. And so one thing that I've been thinking about is how you could apply this in a way that you could kind of get real-time, flexible input in terms of tracking your joint movements. And so applying Clement's technique to tattoo paper, we were able to track relative motion using the joints and be able to kind of move your joint and close your joint, detect that joint information. And so we could also look at, initially, there might be some interaction with gestures that we could use this for, but also the idea is that in the future, maybe it could be used for sports or dance, where you could kind of wear this under your clothing or wear for long periods of time. So the next thing I want to get into is creative spatial interfaces, technologies for creative expression. So what do I mean by creative spatial interfaces? So this term I kind of made up, and so defining it, I think about it in two ways. One is, what technologies can we develop for creative expression? And I'm tying this back to the existing techniques or existing tasks of selection, manipulation, scale, that maybe those don't quite fit in with creative expression. And the other is that maybe you're interacting in a surprising or creative way. So one example I could give is, what if instead of a joystick, you were using chopsticks to pick up an object and rotate and scale and things like that? And so you're probably wondering, well, why would you do that? Well, one might be to practice your chopstick skills, but then the other might be is that you're just making it an experience that's something that's not necessarily for a specific task to do something, but rather for, you know, a creative way to interact with the environment. And so one project that I've been working on with the folks here at Atlas is the XR Jam project, and this particular version of it is the HoloJam. And I'm just kind of doing a shameless plug to see this demo today. they have this set up for the PhD students, and the idea is that you can drum with these holographic characters, and they'll drum along with you. And so in this case, how do you then, the task is not selection, translation, rotation. The task is jamming with these other characters. And so how do you evaluate that? And so that's a question that we're discussing and brainstorming on how to kind of look at those techniques in a different way. And the last one that I'll show you is a project that we've just started where we're looking at how to make food interactive. And so using similar technology that you would use for marker-based tracking and augmented reality, we apply that to food using food-grade edible dyes and markers, and trying to look at what are the different ways that you might interact with it, but then also how tearing apart or biting or destroying or kind of breaking that food can then create new ways to interact and change the virtual information. So then that leads me to kind of what are some of the open questions. And so one of the things that I think about is when I think about this work that I've done with perception, and there's a lot of techniques done by created by other researchers where they kind of use those perception limitations to make magic techniques where if you do something, it kind of changes the virtual information, how you're interacting. I'll give an example. One technique is haptic retargeting, where when you reach out to an object, you're reaching out to a passive physical object, and your physical arm is reaching in the same place each time, but then your virtual arm is kind of moving to the left, moving to the right. And the reason why it works is that because you're resetting your virtual arm out of view, so you can kind of reset the rotational change of that virtual information. So a lot of these techniques work really well in virtual environments because you can't see your real body, but how well do they work in augmented reality is an interesting question to see how they would apply in those contexts. Then the other is looking at creative spatial interfaces. So looking at beyond selection, manipulation, navigation, how do you evaluate what does it mean to have interactive food for augmented reality? What does it mean to have an interface that allows you to jam and get into the zone? How do you look at those in more detail and decide whether you're successful or not? And so some of these things that I've been thinking about recently lead me to this vision that can't do this alone, and we need designers, artists, creators, crafters, makers, all of the above, researchers in tangible user interfaces, 3D user interfaces, VR, XR, AR, and then also domain experts in these various areas that you're applying this to, and looking in this new dimension of 3D user interfaces, of creative spatial interfaces beyond selection, manipulation, scale, rotation, things like that. And how you would design those interfaces, how would you evaluate those interfaces kind of going forward. So this is kind of my vision and my ask to you as far as, think about this in terms of your own work, in terms of the work that I've showed you, and how we might collaborate. Any questions? I'm going to stop the screen so I can see you all.
Questions from the floor, questions in the chat? All right, not just questions, arguments, disagreements, proposals.
I don't argue very well.
Shiva
This
says,
question. So the question is, what have your students at Atlas been up to this semester and last? So some of the students that I've been working with are from the Acme Lab, which are L&D students. And one of the things that we've been working on this semester is looking at the holographic jam project, where we want to see how that compares to using augmented reality glasses. And one of the things that we think that there might be some differences are in the peripheral view. So in an augmented reality glasses right now, the devices only give you a narrow field of view. That will most certainly change in the future. And there are probably researchers working on that exact problem right now, but we want to look at also what does having that peripheral view of the other drummers in the circle kind of give you in terms of communication. Ellen talks a lot about in her drum circle, you nod your head or raise your hand to kind of start the drumming circle, or depending on who you're following. And in that regard, if there's someone to your left or to the right in your periphery, you actually have to physically move your head in the augmented reality glasses. So we want to look at how having the holographic drummers will facilitate in that regard. And then if there is a difference, what can we do to add to the augmented reality glasses in your periphery to give you similar signals and provide that information. And so last semester, students were working on evaluating the spatial audio and looked at sorry, not the spatial audio, but the audio delay or latency, and how you're able to kind of perceive and follow along with those drums. So we did evaluation on that, and that was more of a quantitative evaluation and kind of getting more into the interesting qualitative evaluation. What does it mean to kind of jam with those drummers? What do we know? Okay. So there's another question. What do we know about how people learn 3D interfaces compared to 2D interfaces? Could you elaborate a little bit, Ephraim?
Just that. Is there do you know differences? Like, I don't know. I'm like how do people, like, what's the learning effect? Like how quickly do people get the grasp of how this interface works? It's not always from the get-go, I assume.
Yeah, I think that's very dependent on the specific interaction technique itself. And there's also this debate about what does it mean to have a natural interaction technique? That term is more representative of kind of the innate actions that you've learned since you were younger. So, and interacting with the world around us. So when you go to reach for an object and things like that, those are things that you've learned in the environment. So those experiences, and then certainly if you've learned to interact in a different way in the environment, that may change how you learn those interaction techniques. And one of the really cool examples of kind of changing how we perceive how we interact in the world. There was a researcher group who developed an empathy environment for understanding or producing empathy for those who may have reduced function in their limbs. And so one of the experiences was that you were in this world where you had to do everything with 3 arms, even though you only had 2. And so you had to relearn how to put the ticket in for the train. You had to relearn how to kind of pick objects up and manipulate them because they all involved 3 limbs. And so I thought that was interesting. And so this idea of learning how to interact in 3D spatial interfaces compared to 2D, I think it's based on kind of your experiences, what skills you have coming to the table, and then also the technique itself. So I would say that might be widely different based on the device and the technique. Did that answer your question? Okay, the next question. Would love to learn more on your soft, squishy user interfaces. What other applications do you envision? All for VR or also different contexts? Yeah, absolutely different contexts. So one of the other things that I thought would be great use of that technology is applying it to low-cost prosthetic devices, where you could put the small piece of silicone on the tips of the low-cost prosthetic device, and then it might be able to sense pressure so that you're not kind of crushing an object, and you can apply the appropriate soft or stronger grasp on an object. So that's one other context. But I'd love to talk about other contexts where we could use the squishy device, and I'm happy to bring it one day that if you want to play with it. And so does that answer your question, Daniel?
Yeah, definitely. Thank you. Sounds really exciting.
Cool.
JP.
There's another. Oh, yeah. Presumably users have a mental model of how a VR system works and may be surprised if their performance doesn't match their modeled expectations. How these effects change in AR. Oh, that's interesting. So first, you know, working with a VR system, you know, I think their mental model will depend on what type of input, what type of output you have. So for example, if you're in a VR environment using a head-mounted display and your hands are tracked and you can interact with that way versus if you have a tracked joystick, and compared whether you have real-time tracking at all. And so a lot of factors feed into that and that mental model. And so if that's different, so I'll give you an example. So there's a redirected walking technique where as you're walking around in the physical space, it actually over-rotates you or under-rotates your view. And so your mental model of interacting in the space might be that, oh, I'm walking around just fine. And then you take off the headset and you're in a completely different configuration that you even thought. And so that's where you might have some of that mental model mismatch. And so similarly in AR, maybe because you have real world, that mental model might match a little bit better in that context. So that's one way where I might see those differences between AR and VR.
Thank you. I have a question. In terms of just like technically, like what tools are you using to like your research is more on the AR user experience, but like technically what tools are you using? What equipment? I saw the drum circle had some cool, like almost like you're trying to make holograms. Like,
yeah.
Like what are you using to make that stuff?
Well, that's a great question because a wide range, and I will tell you the types of tools have changed drastically since I graduated with my PhD back in 2008. And so the tools back then, a lot were kind of research, kind of built-in research labs, open source, things like that, but very difficult for students to kind of engage in and learn. So teaching the virtual reality class, I often had to require, you know, advanced levels of computer science, programming skills. I don't have to do that anymore. Often the software tools are Unity, and real various types of modeling software like Blender, 3ds Max, Maya, things like that. And so now there's that barrier to entry is much lower in terms of what skills you need to have to start. And so I've kind of worked with a wide range of undergraduates, graduate students from art disciplines, from computer science disciplines, able to kind of learn how to build interactive systems for VR because of those tools available. On the hardware side, it's also changed drastically. So it went from when I first started at University of Wyoming in 2010, where you would pay a lot of money for one headset that was being built out of someone's garage, and to where now the cost of head-mounted displays and tracking systems is very low relative to that time. They still could be lower, but one of the things that came about that change was having, it started in 2012 with not Google Cardboard, but ICT, Institute for Creative Technologies, their FOV to go. So their field of view to go was like a foam cardboard based viewer that you could put your phone in. And then later on, the socket-based HMD, which then became the Oculus. And so anyway, because of those drastic changes in hardware, now even more, they have tried to simplify it and connect devices across the different brands like Vive and Oculus and things like that. So then when you're writing programs to then represent the input devices for one, like the Vive controllers, then you can, with a few extra steps, you can get it working with the Oculus as well. So that is a really nice advancement as well. And so in my classes, I every year revisit what is the current technology, what should students learn in that field of VR. And then also in my computer graphics course, I used to teach computer graphics with OpenGL and then GLUT. It's a windowing toolkit, but with all of the explosion of using VR technology, I recognized that it was important that students learn those tools. And so instead of using GLUT as a windowing toolkit, I used Unity. But one of the things that I didn't want them to lose was programming with the deep down OpenGL commands that Unity kind of adds layers to. And I figured out how to make those lower level OpenGL calls within Unity. And so was able to teach my computer graphics students that so they can learn both. And so, yeah, every year it's changing, it's different. And so I've worked with a wide range of tracking technologies, electromagnetic trackers, optical trackers, camera trackers, things like that, a wide range of display devices, head-mounted displays, augmented reality displays, monocular, where you have one eye, and cave-based displays. And they're all very different in what they afford, how the experience in VR, AR will be. Does that answer your question?
Yeah, a lot of good examples.
All right, I'm really sorry. It's my very unpleasant duty to cut this off and thank the speaker, Amy.
Well, if you all are on campus, reach out to me. I'm happy to discuss more, just to take a walk or have a coffee or whatever that may be, and chat more.
You're on campus today?
She's right there.
Yes.
Oh, there she is. All right.
Yeah.
Easy peasy.
Yeah.
All right. Well, thank you very much. We're done.
Bye.